Hi everyone, welcome back. So today we're going to start a new series on electromagnetic theory. So this series is a series that I'm developing for a class that I will be teaching at UC Berkeley called Applied Electromagnetic Theory. So it's a graduate level class. So in today's video, we'll introduce what the course is going to look like or what the series is going to look like. And we'll also do a little bit of review of some of the prerequisites in vector calculus that you will need. So it's just to warm you up for the videos that are going to be coming up in the next few months. Okay, so let's get started. So my electromagnetic theory. Okay, so the website for this class is going to be at out here. So you can look at the address. I'll also leave it in the description below. So if you go down here, you can see the information for the class. This is more relevant for people taking it at Berkeley, but for those of you who are watching this on YouTube, I think what's most relevant is the syllabus. So essentially, we'll start with Maxwell's equations, which will be in the next video. So in this video, we're not going to do any of this. Differential integral form, we'll also derive the boundary conditions. Then we'll do wave-matter interactions, so constitutive relations, which is dielectric constant, where it comes from, different models of dielectric constant, which is Lorentz model, Toot model, and so on. And we'll also look at Kramer-Kronig relations when we do dispersion. Then we'll review electromagnetic theorems. So you can see different kind of theorems that we look at. And then we'll move on to potentials. We'll derive the wave equation from Maxwell's equations. We'll derive Green's functions. What is the radiation boundary condition? And we'll talk about antennas. And then we'll move on from there to integral equation approaches. So method of moments is one way to solve integral equations in EM. It's a very useful tool, which you should know. So we won't go into too much detail, but we'll introduce what MOM is. And then from there, we'll derive physical optics and geometrical optics. Following that, we'll discuss plane waves, plane wave, reflection and transmission through boundaries, plane wave propagation in different kinds of media. And then following that, we'll do waveguides and resonators in different geometries, so rectangular, cylindrical, arbitrary cross-section waveguides. And we'll actually look at a cool technique called calculus of variations, which allows you to solve waveguide modes for an arbitrary cross-section waveguide numerically. And in that part, we'll also look at finite element analysis, which is what HFSS, for example, uses, one of the tools in HFSS. And then we'll move on to scattering. So we'll look at scattering from spheres and different kinds of solutions for scattering from spheres. And following that, we will discuss small antennas and some additional topics. I don't know if in the actual class that I teach at Berkeley, I'll get time to do a lot of this, but on YouTube, for sure, we have a lot of time. So I will cover these topics on YouTube. Okay, so essentially, the course will focus on, or the series of videos will focus on the theory. But along with theory, we'll also spend quite a bit of time on HFSS. So I think it's a very useful tool. The reason I'm using HFSS is because I'm mostly familiar with HFSS, and also it has many different tools. It's not good only at one thing. So we'll look at how to use the different solvers in HFSS to do a lot of CAD as well. Okay, so the textbook for the class is we're using Foundations of Applied Electromagnetics by Kamal Saravandi, who was my PhD advisor. And one of the reasons I'm using it is because there's a free link available for this book that anyone can use and download. So on this website, you can go and click on it and download the book. There are also many useful reference books that I've listed here. Some topics will cover from the reference books, but most of it will be coming from the textbook. Okay, and as I say here, the lecture recordings will be posted on YouTube, and my notes will be posted on this website down here, maybe somewhere here as we go through it. Okay, and the rest of it is relevant more for the class, so I'm not going to talk about that here. Okay, so now that I've kind of introduced this class, hopefully you're kind of motivated and excited. and we can jump into the prerequisites. So if you open this notes, the supplementary notes, you can see this is where I'll be adding things as we go through the class. I might not add notes here because I don't have printed notes yet. Right now it's kind of handwritten, but over time maybe I'll add more to this. So you can go through all of this. This is fine. So this is where we'll start off. So we'll do some prerequisites in vector calculus. There are several YouTube videos that I highly recommend, a YouTube series that I highly recommend on vector calculus. These are more like introductory, I would say. They're not very technical. And the same for linear algebra. So you can kind of go through these lists and see if you want to learn from the basics. But let's assume you've taken a vector calculus course in the past and you just want to review it. And that's what we'll do today. So we'll kind of review these derivations for all these coordinate conversions, the unit conversions. And I'm not going to do this part. We will do this, so differential length, area, and volumes, and we'll maybe talk about some of these relationships. Okay, so enough about that. Let's go back and go to our writing board and then start from there. Okay, so we are going to do a review of vector calculus. So I'm not going to be very rigorous. I just want to give you some intuition behind some of these relationships and where they come from, just to get you warmed up for the class, basically. Okay, so that's fine. Start with gradient, right? So gradient, hopefully you've seen what is known as the del operator, right? That's in Cartesian coordinates, it's ddx, ddy, z. And in some sense, it's kind of defined by this gradient, right? So if I have a scalar function f, which is a function of position, scalar, what I mean by scalar is it just takes one real value at every point in space. And the gradient is defined like this. So this is the definition. It is the limit as h tends to 0, f of r plus hv minus f of r divided by h. Right, so this r here is the position vector. So let's say I have some coordinate system x, y, z, right? So my r is this position vector. So I'm saying, okay, at this point, I know what the function is, which is f of r, right? I take a small deviation, add another vector to it, hv, right? And that gives me a new vector here, and the function there is f of r plus hv, right? So I find how this function changes from this point to this point, right? So I find how the function changes from here to here, and as this vector becomes smaller and smaller, you converge to some value, and that's essentially the directional derivative of this function along the direction v, right? So the gradient, essentially when you dot it with this vector v, it gives you the directional derivative in that direction. So in some sense, the gradient is a vector, right? It has three components, and you take each component. So let's say this v is x hat, then you get the gradient, and you get df over dx, x hat, right? You get the component along x hat. So you take the different components, you add them up, and that gives you this vector gradient. So this essentially describes how, in which direction a given scalar function is changing the fastest at every given point in time, in space, right? So, a simple example is that, let's say you're going hiking, right, in the hills of Berkeley. You stand at some location, right? The elevation of the hill is a scalar function. It has a position, 2D scalar function, right? Now you look around you and you find which direction is the steepest ascent, right? Let's say, this is the hill. This is a 1D hill. You're standing here. You want to find which direction is the steepest ascent. Let's say it's this direction. And that's essentially what the gradient is. It's telling you in which direction the function is changing fastest and by what value, right? So there's a direction and a value, and that's why it's a vector quantity. Okay, so that's about gradient. Then there is another important quantity called the divergence. So divergence is del dot A, where essentially you have a vector field now. It's not a scalar field. So at every point in space, you have a vector. That's what gives you a vector field, right? So, this is a vector field, for example. At every point, there is some direction. So flow of water is a good vector field, and we'll see that electric and magnetic fields are vector fields. And hopefully you've seen that before, but if you haven't, then that's what it is. And if you're given a vector field A, you can compute at every point in space its divergence, and that is defined as the limit when delta V goes to 0, 1 over delta V, surface integral A dot ds. So what does this mean, right? So at every point in space, let's say this is a point in space, I can form, I look at a small volume around it. So let's say you've put a small ball around this point in space, and then that ball has a surface S, right? You take a small patch on that surface, and that patch, of course, has a orientation, right? It can be oriented in some point, some direction. So that orientation is defined by a vector, which is ds. Okay, and the value, the magnitude of this vector is defined by the size of the patch. The direction of the vector is defined by the normal component at the center of that patch. That's what this ds vector means, right? So what you're doing is you're trying to see, okay, along this patch, on this patch, if I look at the vector A, say the vector is in this direction, A. By taking the dot product of this A with this ds vector, you're essentially trying to see how much of this vector A is leaving that patch, right? So if the dot product is very high, that means that A and ds are in the same direction, which means this vector field is kind of exiting that ball at that location. Whereas if the dot product is 0, that means the vector field is kind of tangential to that patch, right? So it's tangential to that surface, so it doesn't really leave the ball, right? So by putting this ball around and by calculating at every small patch, so you take different patches of different sizes, right? You see how much of this vector field is leaving at every single patch, you add them all up, and that gives you this integral. So that gives you an idea of how much of this field wants to leave this ball, right? And as the size of this ball becomes smaller and smaller, which is what you're doing here by taking this limit, you essentially come up with a value called the divergence. And that tells you how much of this field at this point is diverging away from this point, right? So that's the idea behind divergence. And it's a very useful quantity, as we'll see. It gives you some idea of what is inside the ball, basically. That's what divergence means in some sense. Okay, so hopefully that makes sense. And of course, you can compute this easily in different coordinate systems, which we'll look at the equations for computing it. But that's what the intuition behind divergence is. And the last important quantity is curl. And so the idea is something similar. So curl is del cross A dot n hat. And that is defined as limit as delta s goes to 0, contour integral A dot dl divided by delta S. So it's very similar to our earlier definition, but let's look at what this means, right? So once again, in this case, since we're dealing with a contour integral, take a surface basically. Okay. So let's say again you have a vector field. Again, we're dealing with vector fields here. And what is dl, right? So dl is take a small section of this contour and you look at what the tangent is, that section, right? So that has a direction, of course, and it has size based on how much, let's say this length is dl, right? So now in this case, when you take a contour and you want to, or a surface, sorry, a contour, and you define dl, then it is tangential, unlike the normal case, right? And now you want to see how much of this vector field is going along this tangent, right? So that's why when you do a dot dl, get a large value, the vector field is leaving this contour, then a dot dl is 0, right? That is normal to the contour. And you do it at all locations of this contour, and that gives you essentially how much of this vector field is circulating around this point, right? And that's what this kind of contour integral means, is that at every point you do this dot product, and then you add them all up like an integral, and then you send the limit as the size of this patch. So the size of this patch is delta S. If you send the limit as the size goes to 0, and that essentially gives you a quantity, which is a vector. Right? The reason it's a vector is that you can have circulation in two different directions. Right? You can have a circulation this way, which gives you a direction, let's say coming out of the page, or you can have even circulation in the other direction. Right? Now this is for a 2D patch. You can actually define curl, in fact, is defined in 3 dimensions. If you have a 3-dimensional vector field, it's a little bit more complicated, but essentially what you can do is you can make 3 patches with 3 different normal components. So this patch has a normal component coming, let's say, out of the page. Right? So when I take the dot product, it gives me one component of this curl. Right? So this gives me the component that is normal to the page. Then I have to take another patch that is oriented. Let's actually put an axis here. So let's say this is X and Y, right? So if I take another patch, which is in the YZ plane, I mean, it's hard to draw it here, I guess, but essentially it would look like a line in this plane, right? But in the YZ plane, it would look like another patch. Then you find what is the curl, this dot product, that direction. You take the XZ plane, and that gives you curl in the third direction. You add up those 3 components, and that gives you the actual curl. So this actually gives you a vector field, say B. Right? B is curl of A. Now you can calculate component-wise using, this relationship, right? So that's kind of the intuition behind what curl is and why the definition looks like this. Okay, so although this is kind of the definition of these 3 different identities or values or quantities, we don't usually use these definitions to calculate them. So to calculate them in different coordinate systems is easy, and we'll discuss coordinate systems next to have a better understanding of what they are. But essentially, in the supplementary notes, I have a couple of tables that you can use to calculate them. So here they are. So the gradient, divergence, curl, and Laplace operator, we'll see what that is. That's essentially the divergence of the gradient of a field. But you can calculate them fairly easily using these tables, right? And they're fairly standard. So given a function, a vector, a scalar function, you can just apply these formulae to calculate. So this is in spherical coordinates. Okay, so let's actually discuss coordinate systems. I think it's important to have a good understanding of electromagnetism. You need to understand coordinate systems. You have a good intuition of coordinate systems. So let's do that next. Okay. Hopefully, a lot of this is kind of a refresher review from, let's say, your undergraduate uh, vector calculus class or your undergraduate electromagnetics class. But if you haven't taken those classes, you can go through the video sources that I provided in the supplementary notes and kind of learn this stuff fairly quickly. Okay, Cartesian coordinates named after Descartes, of course, are in some sense the simplest and most intuitive. You have your standard x, y, z. Right? And the reason I define them this way is that you want x cross y to be along z. It's called a right-handed coordinate system, right? Because you take the right hand, your fingers are pointed, say this direction, do your right hand rule, take x cross y, that gives you z. Okay, so this is simple. X is nothing but x, y is nothing but y, z is nothing but z. Obviously, x hat is also x hat, y hat is y hat, and z hat is z hat. It's very trivial, right? The reason I'm writing it this way is because when we do other coordinate systems, you'll see that we need to develop some relations. Okay, so that's about Cartesian coordinates. Very simple. Next coordinate system is cylindrical coordinates. So what are these? So this looks something like this. So you have basically, we'll use our Cartesian coordinates as kind of a reference. See, okay, so cylindrical coordinates, essentially, it's like having a cylinder on there, right? In the XY plane. I'm not very good at drawing this correctly, but you can imagine a circle in the XY plane, and then Z axis is like the cylinder, right? Okay. So there are three components. So we define radius, rho. Actually, let me use a different color. So radius of the cylinder is rho. And then, actually, let me draw it here. So every point in space can be defined instead of an XYZ coordinate by a rho coordinate, phi coordinate, which is its angle with the x-axis, and then a z coordinate, right? So in the xy plane, you define based on rho and phi, and the z plane is just kind of translated up and down. Okay, so apart from just this rho and phi, we also have unit vectors. So I'll call this rho. So at every point in space, you have a unit vector. So there's a unit vector rho hat, which is like that. We'll define exactly how this rho hat is looks like. And then you have a phi hat, and then your standard z hat, which goes around z. Okay, so let's find the relationship with Cartesian coordinates. So of course it's a circle. So the value of rho is nothing but x squared plus y squared, right? So every point rho, you can drop lines to x and y. So this is the x coordinate value, that's the y coordinate value. And since it's a circle, rho squared is x squared plus y squared, right? And phi is also very simple. It's tan inverse of y over x. And that's also easy to see from simple geometry, is that this is also y. So you take the tangent of this, and that gives you y over x. You need to be a little bit careful when doing tan inverse. Not to get into details now, but you need to be careful about the domain and range of tan. So when you're using MATLAB, you'll use the atan2 function, for example. So just keep that in mind. And of course, z is the same as z, right? So we can also write the other way around, where x is nothing but rho cosine phi, y is rho sine phi. Again, simple relationships for a circle, and z is nothing but z. Okay, so the next thing is to write down the unit vectors. Okay, so how do you write down rho hat? right, in terms of x hat and y hat. Okay, so you can see that this rho hat, as you go around this circle, it becomes x hat when you're along x, right? So when y is 0, which means you're along the x-axis, rho hat should be equal to x hat. When x is 0, which means you're along the y-axis, rho hat should be equal to y hat, right? Because as you go around, sort of this normal moves around, and you end up with that. Okay, so that's why, rho hat is nothing but x hat plus y hat. And if you divide this by square root of x squared plus y squared, because you want it to be a unit vector, right? So only if you divide it, you get this to be a unit vector. You're kind of normalizing it to the length of x hat plus y hat, right? And now that you know how to write x in terms of rho and phi, you can write this as cosine phi x hat plus sine phi y hat. Right? So all I've done here is I've substituted x and y from these guys, and you'll end up with this relationship. Okay, that's nice. Now when it comes to phi hat, so we want, in every coordinate system, we want the unit vectors to be orthogonal in space, right? So essentially, if my rho hat is always pointing normally out in this circle, and I want my phi hat to be tangential at every point, right? Something like this. And of course, there are two options. You can pick tangential this way, or you can pick tangential this way. But by convention, because rho is growing this way, or sorry, phi is growing this way, we choose tangential direction to be like that. Okay. So, of course, it's fairly easy to see this. Now, if you want rho hat dot phi hat to be 0, there are two options. And the option that is along the growth of phi is minus y times x hat plus x times y hat divided by square root of x squared plus y squared, right? You can quickly see that. I mean, if you take the dot product, you get minus xy plus xy, and that gives you 0, right? Okay. And once again, you can substitute, and you end up with minus sine phi x hat plus cosine phi y hat, right? Okay. And of course, the last relationship is nothing but z hat, which is Cartesian coordinates. It's just z hat. So that's nice. Okay, so now that we have these relations, we would also like to derive the other direction. So how do you write x hat in terms of rho hat and phi hat, right? And you can quickly do that from these equations. So you have two equations, two unknowns. You essentially want to invert them. So it's fairly easy to see if I multiply this with sine phi. If I multiply this with cosine phi, this with minus sine phi, and I add them up, then that gives me x hat, right? Because sine square phi plus cosine square phi is 1, and the other term cancels out. So it's fairly easy to see that x hat is nothing but cosine phi rho hat minus sine phi phi hat. Y hat is sine phi rho hat plus cosine phi phi hat. And you can do the same thing even with this and this relationship. So multiply with y on top, multiply this with x, then add and subtract. That again gives you simple relationships, which is in terms of x and phi, but x and y and phi hat and rho hat. Right, so that's x rho hat minus y phi hat divided by square root of x squared plus y squared. And we have y hat is equal to y rho hat plus x phi hat divided by square root of x squared plus y squared. Okay. So we've developed relations for the position vectors and the unit vectors, right? Position vectors and the direction vectors. Okay, so the last one is spherical coordinates. Maybe let's do that next. So we are going to use what I call spherical polar coordinates. You need to be a little bit careful about this. There are different ways to define spherical coordinates. Okay, so what is spherical polar coordinates, right? So in spherical polar coordinates, maybe let's go to a new page. Okay, that's fine. Do it here. So you have, again, in terms of Cartesian, x, y, z, right? And I have a position vector. Say this is r vector, right? That's my position vector. Now the length of this is r, right? And then there are three angles. So the first thing you need to do is you need to project this vector onto the xy plane. Okay, that projection is, the projection in the xy plane. That projection makes an angle phi with the x-axis. So you define one angle with that. And this vector, which is r vector, also makes another angle, theta, with the z-axis, right? So that's called the polar angle. So this is polar angle, and this is azimuthal angle. Sometimes spherical polar coordinates are also defined by the angle that this vector makes with the xy plane. So that would be 90 minus theta, right? So that's called the elevation angle. So you just be a little bit careful about the difference between spherical polar coordinates and spherical coordinates that are defined with an elevation angle, right? So they can be, the equations can be different. Okay. Now we have, again, this is the position vector, but you can also have a unit vector at this location and three unit vectors, I guess, which are direction vectors. So there's the r hat, which is radially going out. So it's a unit vector that goes basically radially out from this position vector, right? So you go along this line, you reach this point, and then you draw a unit vector at that point, and that's r hat. Now it's a little bit tricky to draw it here, but there are two more position vectors. So there is one which is phi hat. So what you do is similar to what we had earlier. You have this projection into the xy plane. At that projection, you can draw phi hat because that's essentially now on the xy plane. It's similar to your cylindrical coordinates. So you can draw phi hat there, and then you can translate that back up there, right? So essentially, it is in the direction of as phi is growing. So essentially, it's tangential to this imaginary circle on the xy plane, and and that can be moved up to this point, and that gives you a phi hat. So I don't know, it might become too cluttered if I draw it here, but maybe I can try. So that's your phi hat. Okay. And the other angle is theta hat, right? So as theta is increasing for a fixed r and a fixed phi. So you fix r, you fix phi, and then you move theta. So what happens when you do that? When you do that, this position vector starts to move down like that. So you have to kind of imagine that. Imagine that this is a rod, its length is fixed, its azimuthal angle is fixed, so it can only move kind of straight down like that, right? And that defines our theta hat. Theta hat. Oh, sorry, that's okay. Okay, so if you look at basically that point from above, you will see kind of a projection of r hat going that way. You will see phi hat going this way. This is phi hat, right? So what I'm looking at now is kind of looking down from above. I can see the XY plane. I can't see Z axis. And that's why your theta hat now is going to look like it's going into the page, right? So that's your theta hat. Circle with the cross means into the page, dot, circle with the dot inside means coming out of the page, right? Okay, so it's a little bit more complicated, I guess, but once you understand it and use it quite a bit, it becomes actually very easy and intuitive. Okay, so of course R, now since we're on the surface of a sphere rather than the surface of a cylinder, so R is nothing but square root of x squared plus y squared plus z squared, right? Theta is tan inverse of rho over z, and that's fairly easy to see, is that when you take this, so let's use a different color, right? So this line that I've drawn here, if I translate it up, it would basically be this line. And it doesn't look like that, but maybe I can actually make it look like that. It would be kind of that line, right? And the length of that is nothing but rho. So tan theta is rho over this length, right? Because this would be a right angle. Okay. So that is nothing but tan inverse of square root of x squared plus y squared over z. Okay, and phi is the same as before because it's the same for cylindrical coordinates, nothing but tan inverse of y over x. All right. So we can go the other way as well. So we can write x as, so this rho, right, this length rho here, this image is getting kind of cluttered. So I'm actually do this. So this rho is our sine theta, right? And it's the same reason is that this is theta, this is 90 minus theta. So this value is nothing but cosine of 90 minus theta, which is sine theta, right? So since rho is r sine theta, and we know that x is nothing but rho cosine phi, x is r sine theta cosine phi, right? That's nothing but rho cosine phi. Y is r sine theta sine phi, which is rho sine phi, and z is r cosine theta. It's just a projection onto the z-axis, right? Which would be this length here. Okay, so that's about that. Let me quickly make a copy of this diagram down below so that we can continue with the unit vectors. Okay, so there it is. Now we want to define r hat, theta hat, and phi hat. So r hat is xx hat. It's the same idea as before. Y hat plus zz hat, which is that when you're in the, when y and z are 0, r hat points along x hat. When x and z are 0, it points along y hat, and x and y are 0, it points along z hat, right? Divided by square root of x squared plus y squared plus z squared to normalize it. And that gives me, I can replace x, y, z from what we just derived. So that's sine theta cosine phi x hat plus sine theta sine phi y hat plus sine theta z hat. Okay. And now comes a little bit trickier part, which is theta hat. So what's the intuition behind theta hat, right? So when z is 0, right, which means this thing is now lying on the xy plane, you can kind of see that this theta now is pointing along minus z, right? Because it's pointing away, sort of normal to r and phi. And when you bring this down, and that vector is on the xy plane, then theta has to be along minus z. Right? Whereas when theta is 0, which means you're along the z-axis, right? Then where does theta point? When theta is 0, theta hat points along rho hat. Right? It's kind of radially outward. It's actually not well defined at that point. Right? So when you're kind of getting closer and closer and closer, points along rho. So this point is there. This is I'm looking at basically from above. So when I look from down here, this is what I see, right? Your theta points along rho hat basically. So that gives us a clue that it should look something like this. And again, obviously, we want to normalize this, right? So when z is 0, which means you're on the xy plane, it's along minus rho. It's along z hat, minus z hat, right? So when z is 0, it's just minus z hat, and when rho is 0, it's rho hat, right? Okay, so now we have relationships for all these guys. We can put them in. We know what rho hat is in terms of x hat and y hat. So this is nothing but z x hat plus y hat minus x squared plus y squared minus x squared plus y squared z hat divided by square root of x squared plus y squared times square root of x squared plus y squared plus z squared. Right, so this denominator term basically became that. When you write rho hat, you will get x hat plus y hat divided by square root of x squared plus y squared. So that's where this came from. And then this square root of x squared plus y squared is multiplied with the square root of x squared plus y squared here to give you this term. And the z comes from here, right? So it's just basic algebra, basically, once you make the substitutions. Okay. And phi hat is the same as before. As we said, it's just a projection onto the xy plane and then cylindrical coordinates. So you just get minus y x hat plus xy hat divided by square root of x squared plus y squared. And that's nothing but minus sine theta x hat plus cosine theta y hat, right? Okay. So now that we have these relationships, again, you have three equations, three unknowns. You can derive the other direction, which is x hat, y hat, and z hat in terms of r hat, theta hat, and phi hat. I'm not going to do that here. And you also don't really have to do that. The relationships can be found in these tables. So we've derived most of these relationships. We left out a couple of them, but basically you can derive them. Right, we derive this. And you can go backwards and also derive. No, we did not derive this actually. This is what we did not derive. So you can derive this by going backwards like we did with the cylindrical coordinates. Okay, that sounds good. It's a good review of most of the things. The last couple of things left over are differential, displacement, surface, and volume. And these are actually really important to understand well. So let's do those. Displacement, length, and volume. Okay, so what do I mean by that, right? So we already looked at this when we're looking at the intuition behind curl gradient and all that. So we said that a small displacement in length, right, is in Cartesian coordinates, it's fairly easy. It's just dx x hat plus dy y hat plus dz z hat. Okay. And that's okay. Cartesian coordinates is very easy to see because you have, let's actually draw it out, x, y, and z. You take some small length, right? Some direction, and that can be decomposed into x, y, and z components. And I can't draw the other one, but get the idea, right? So you can do this dx x hat, let's say this is dz or dy y hat. And then you can also decompose it into projection along z hat, and that gives you the dz component. Okay, that's in Cartesian. Now in cylindrical polar coordinates, we have d rho hat plus rho d p p hat plus d z z hat. So what is this? Why is it not just d rho hat, d phi phi hat, and d z z hat, right? The reason behind that is that, where you place this dl component will change things. Right, so let's take the xy plane. So let's say this is x, this is y, right? So if we take a small angle, say, take a small angle d phi. Again, I want to find what is this length of a small vector. Now it depends on how far you are. I mean, if I'm here, d phi just gives me this length, right? Small amount of length. But if I'm out here, the same angle, d phi, can give me a larger length if I'm not careful. So I need to actually scale by the radius rho. And that's what the scale factor is. Now, units wise, of course, that makes sense because p is an angle and rho is a length. dl is also a length, so you have to have that rho factor in there. The intuition behind it is that if I have a small differential length dl, then let's say this is dl, then it depends on where it is. I mean, if it's very close by, then the angle that it subtends will be much larger, right? Which means this rho, since rho is smaller, d phi has to be much larger. That's another way to look at it. The angle that this thing subtends is larger than the angle that this subtends. Right? The product of those two has to be constant for this dl value to be constant, right? So it depends on where it exactly is, what the rho value is, and that's why that factor kind of comes in. Okay, so that's about differential length in cylindrical coordinates. Now in spherical polar coordinates, a little bit more technical. dl is dr r hat. That makes sense, right? It's r d theta hat plus r sine theta d phi p hat. And once again, this should make kind of sense. Is that this is nothing but rho, right? So along phi hat, this is the same thing as what we had earlier, which is rho d phi hat, right? Just this. So when you project it down, you have to be a little bit careful by adding this r sine theta term. And along theta hat, it doesn't really matter. You don't really care about the value of this sine theta, but it's the same as here. So in this case, if this is z and this is, let's say, rho, then I'm in the same situation, right? I have a small angle, which is now d theta, it's rho d phi. And depending on how far I am from the center of the spherical coordinate system, the length that this angle subtends changes. So that's why you need to multiply it by the scale factor r, right? And that's why dl has this form. Okay. The next one is surfaces, oriented surfaces, ds. Right? And this is also fairly easy to see. X hat, it should be dz dy. as dx dz y hat as dx dy z hat. Okay, so why is that? So maybe we'll do xy plane first. So z hat would be pointed along z, which means the surface it's associated with should lie in the xy plane. This is the xy plane. That's the surface in the xy plane. Now the normal component comes out of the edge, z hat, and this is nothing but dx, and this is dy, right? And the same for the other two. So x hat is along x direction, and that's in the yz plane, so you need dy dz. In the same way, y hat is in the xz plane, so you need dx dy. Okay. This is probably the part which is most confusing, which is oriented surfaces in cylindrical and polar coordinates, spherical coordinates. So let's do for cylindrical. So the coefficient for rho hat is rho d phi dz rho hat plus d rho dz phi hat plus rho d phi d rho z hat. Okay, so why is this? So if you want to look at rho hat, let's take rho hat for example. So essentially now again I'm in the xy plane. So an oriented surface along rho hat has a small length that it subtends in the xy plane, and it has a height, right? So this is the xy plane. Now if I draw, obviously all of this would be much easier to do in 3D, but so if I'm drawing, let's say x comma y in this axis, which is just the rho axis, and I draw z axis like this, and it looks like this, right? Where this cut here is this line here, right? And what's the length of this cut? So we said that differential lengths would have to be multiplied with this rho factor, right? Because the angle that it subtends. So this is nothing but rho d phi, right? Where the small angle is d phi, and rho is how far it is from the origin. And this length here is dz. And that's why you have rho d phi dz as the coefficient of this unit vector. So that's the unit vector rho hat. That's the orientable surface there. And if the orientable surface is along phi hat, which is this, and that surface has one component this way, and the other component in z. This is nothing but d rho, right? This length is d rho, and the other component is dz. That's again very easy to see. So it's like that. Now, if it's along z hat, then it's easy. Then in the xy plane, have a small orientable surface. Let's say something like this, right? So you need to have d rho. Actually, I should draw it as an arc, something like that, right? So this length is d rho, right? And this length is rho d phi. So that's why orientable surfaces in the xz plane, which is along z hat, is rho d phi d rho. Okay, so if you're seeing this for the first time, it can be a little bit technical, but if you spend some time on this, it makes sense. And the last thing we are left with is spherical coordinates. Let's do that in a new page. So once you understand spherical coordinates, everything's trivial, right? So what is orientable surfaces in spherical coordinates? It's r square sine theta d theta d phi r hat plus r sine theta dr d phi theta hat plus r dr d theta d hat. Okay, so let's break this down. This is probably the hardest part of this video. Okay, so let's say we are going along r hat, right? So we want to make an orientable surface along r hat. How do you do that? So we have our x, y, z coordinates, and this is my position vector r. I'll just exaggerate it, and sorry, this is my position vector r, and r hat we know goes along r, right? So it's kind of tangential to that sphere, normal to the sphere defined by this r vector. So if you want to make an orientable surface here, you need to have something that looks like this, right? It's sort of a patch on this sphere. So I'm going to try and draw it. It looks something like this. Maybe something like that, right? So you have this big sphere out here, big sphere, right? I'm taking a small patch out of that sphere. Okay. So what is this length? So this length, we can project it down onto the xy plane. And once you project it down, that's nothing but rho d phi. And what is rho d phi? It's r sine theta d phi, right? So that's one part. That's this length, r sine theta d phi. And what is this length? This length is r d theta, right? And that's again from the differential length that we looked at, is that length is variation in theta. So when you change theta a little bit, the angle that it subtends, the length that it subtends is a factor of r as well. So you have to have that scale factor of r in there, right, to make that, to get that length. So when you take the product of these two to find the area, you get this term. So that's along r hat. So when you take an orientable surface along theta hat, what do you get, right? So let me actually make a copy of this. Stuff. Theta hat, let's say in this case, is kind of going down, right? That's your theta hat. So a surface there is, it has a component that is like that, and it has a component that's kind of going into the page, let's say, right? So when you project that onto the xy plane, that component going into the page looks like an arc, right? So it's kind of hard to visualize it, I guess, but maybe you can visualize it, right? So you take this theta hat, which is normal to perpendicular to this r vector, and you try to orient a surface that's normal, that's basically normal to theta hat. That'll have a component along r, which is this. That's nothing but dr. And the other component which is going into the page, when you project it down around the xy plane, it has a small arc. The length of that arc is rho d phi. That's nothing but r sine theta d phi. So you take the product of those two things, and that gives you this r sine theta d phi times dr. Okay, the last one is an orientable surface that is along phi hat. So in this case, it's actually a nice figure. So phi hat is kind of going into the page, right, or going into the page in this case. That's phi hat, which means an orientable surface looks like this. Maybe not exactly like that. That's something like that, right? So you have the dr component, which is this, and this is nothing but r d theta, which is what we saw earlier as well, right? Which is what we saw here. So you get nothing but r d theta for the phi hat. Okay, so that's how you kind of define orientable surfaces in spherical polar coordinates, right? So you need to know this because when you're doing integrals over surfaces, you need to know how to use these expansions correctly, right? When you're calculating stuff. But once you kind of understand this to some extent, it should be fairly simple. Okay, the last part is orientable volumes. It's actually easier because it's a scalar quantity. It's not a vector. So dv, of course, this is just a cube in space in Cartesian coordinates, and that's dx dy dz. It's easy. And then you have dv in cylindrical coordinates, and that is d rho. Take a small cylinder. It doesn't have to be a small cylinder, actually. It can be a small sector, right? So let's say I take a small sector like this, and I make a volume. So this is in the xy plane. And the z is just z. So this length we saw was nothing but rho d phi. This length is d rho, and the other length is dz. So you get d rho times rho d phi times dz, which is d rho d phi dz. And in spherical polar coordinates, if we go back here, it's essentially this patch. To convert it into a volume, you can kind of extend the patch to a small kind of volumetric element there, right? So it's like taking three components. One component is this, which is the r d theta. The other component is this, which is r sine theta d phi. The last component is along the radius, so it's along r, so it's dr. So you get nothing but dr times r d theta times r sine theta d phi. And that's nothing but r square sine theta dr d theta d phi. Okay, so that's about it when it comes to coordinates. Okay, so hopefully that was somewhat intuitive. You have to obviously spend time, do problems on these things to really internalize them well. But this is probably a good start, a good refresher from your previous classes or previous exposure to this material, right? Okay, so we've covered basically, so far we've covered these relationships in the beginning, then we did the unit vectors, and then we kind of spoke about the general formulation of this. I haven't actually derived these. You don't really need to know. I think it's good to know at least once, but take too much time here to kind of derive why in different coordinate systems these expressions turn out to be this. And lastly, we also did differential displacement, area, and volumes. Right. So the last part is kind of going through some of these vector calculus identities. I can actually do it right here. Okay, so let's do that. So maybe we'll start with these ones. So these are very important, right? So curl of gradient is 0, and that kind of intuitively at least makes sense. Here I'm just going to focus on the intuition and no proofs. So if I take the gradient, it's essentially showing me at every point where things are moving out. So gradient at this point is going to be there, there. So when you take the curl of a field like this, it doesn't have any curl, right? Intuitively, of course, it's not rigorous, but intuitively, you take gradients kind of diverge in some sense, so they don't have any curl. And the same thing when you calculate the curl, you get a field that's kind of like rotational. Every point it's kind of turning, because that's what you're calculating when you take the curl, is how much is the field turning. You don't care about the other component. And that's why the divergence of that is 0. Proofs of these are actually fairly easy. You can easily prove them in the different coordinate systems by using the tables earlier. But you can also actually have a general proof using index notation, which I'm not going to talk about here. Okay, next is Laplacian. So scalar Laplacian is fairly easy. It's just second derivative in each coordinate. So we have it out here. Yeah, here, right? So that's what it is. There are expressions for it. But there's also something called a vector Laplacian. It's in Cartesian, which is this. This is the vector Laplacian. So doing Laplacian of the vector. So Laplacian is this del square operator, which is the divergence of curve, divergence of gradient. So in Cartesian coordinates, we'll see this actually when we do during the course. In Cartesian coordinates, the vector Laplacian actually is nothing but three scalar Laplacians dx of dx ax x hat plus del square ay y hat plus del square az, right? So it actually expands out nice and cleanly like this, where each scalar Laplacian is given by this or the tables above in different coordinate systems. But in cylindrical and polar coordinates, it doesn't actually expand this way nicely. So in cylindrical and polar coordinates, actually, this is the definition of, in some sense, the vector Laplacian, which is the gradient of divergence minus the curl of the field. Okay, so this will actually be quite useful to us. So let's keep that in the back of your head. Okay, then we have product rules. Of course, this is nothing but the chain rule in vector calculus. You remember what that is. This is actually a useful relationship, divergence, both of these. So the divergence and curl of a scalar field times a vector field, right? And it's not as simple as just pulling this out. That's this component, but you also have to take the gradient of that field. Okay, in this case, gradient times cross product of the gradient and the field itself. Okay, then there are some more relationships. And don't really need to prove them. You may not even use these as much, but these are also important to just have in hand. Right? You don't have to prove them, but just you might need to use them at some point. And of course, you have what's known as the back cab rule, which is the cross product of three vectors. And it's very important to keep in mind that cross product is not associative, right? So what does that mean? So that means that these brackets are very important, right? So what I mean by that is A cross B cross C is actually not equal to A cross B cross C. It's not associative. So you have to first calculate this and then cross with this, right? Yeah. So if you're given this, you have to first calculate this and then cross it with C. If you're given this, first calculate this and then cross with B. These should all be vectors, right? So even here, these brackets are important. You need to first calculate that dot product and then multiply with B. Actually, no, in this relationship, it doesn't matter, I think, because when you calculate the dot product, you get a scalar. But you just need to be careful about the order of terms. Okay, and yeah, these are also useful relations to have in mind. And of course, we've seen this before, is that A cross B is minus B cross A. And you can use these simple relations to derive all these guys as well. Okay, so moving on to integral relations. This is a very important relationship. So this is the fundamental theorem of line integrals. Is that when you take the integral of a gradient along a certain direction, not along a certain, yeah, along a certain direction, this is nothing but the directional derivative, right? Del dot phi dot dr, or gradient of phi dot dr is nothing but the directional derivative of phi along r, right? And we kind of saw that in the beginning. So this is very useful actually. This theorem actually defines what a conservative vector field is, right? And we'll maybe see that at one point in the class, or you've seen that before. So it's important to have in mind. And it's fairly easy to see is that you take an integral of a gradient that's like very, very loosely speaking, canceling out that integral and gradient, and you're left with just the function itself, right? But that's super non-rigorous, but yeah, the relationship itself is quite rigorous. Okay, the next one is the divergence theorem. So having good intuition of divergence theorem is super useful. So what is this saying, right? So let's see what it's saying. If I have a volume, say this is a volume V, and I have some field inside this volume A, vector field. I calculate its divergence. So every point I see how much of it is kind of leaving that point, right? You calculate the divergence at every point and you add up all those divergence values along the entire volume, every point in the volume, and that gives you the left-hand side. The right-hand side is saying all I need to do is I take patches on the surface of this volume. So that's a patch on the surface. That's a patch on the surface. It's a patch on the surface. And I find how much of the field is actually leaving the surface. So the bounding surface of this volume, how much is leaving? And that's what this A dot ds is, which we saw in the beginning as well. I add up all those contributions, and that's the same thing as what we did on the left-hand side. And the reason behind that, in some sense, the idea behind the proof of this is that when you take divergence between two neighboring points, right, any field that's coming out of here will show up as a negative divergence of the field at this point, right? Because divergence here is coming out, whereas divergence for the point next to it is going in. So when you add them, this actually cancels out. So when you take two neighboring points, these divergences can, I can write a bigger point here, take a point here. This divergence is this way, this divergence is this way. Point here, this is this way, this is this way. So you eventually just cancel out all these internal contributions, and you're left with nothing but a surface contribution where there's nothing to cancel it on the surface, so it just leaves. And that's the idea behind this divergence theorem. And it's really powerful. We'll see. It's really, really useful. Keeps coming up all the time, so it's important to kind of keep that in mind. The other super useful relationship is called Stokes' theorem. It's a special case of the generalized Stokes' theorem, which is the same idea or similar idea. In this case, you have not a volume but a surface, and you have calculating the curl at every point. That you add up all these contributions of the entire surface, that gives you the term on the left-hand side. On the right-hand side, you're just calculating the tangential component of this vector field on the entire surface, and they're equal. And again, it's the same idea, is that you have curl this way and you have curl this way. These components cancel out, right? It's the same with this and this. They cancel out in the opposite direction. They cancel out. So you're only left with the contribution from the edge, which is the contour integral that you have on the right-hand side. Okay, so that's the idea behind divergence in Stokes' theorem. You can do the same thing in volume as well for Stokes, which is the 3D Stokes theorem. These are actually special cases of what is called the generalized Stokes theorem. I'm not going to talk about that here. It's not really relevant for this class, but it's actually a very beautiful piece of mathematics which shows that from differential manifolds, which shows that these relationships are actually special cases of a very general manifold relationship called the generalized Stokes theorem. And understanding that, again, this is kind of a tangent, but understanding that actually will give you a deep intuition of integral and differential calculus and differential forms and so on and so forth. Okay, then we have this identity called Green's identities. There are two of them. We derived this in class, so I'm not going to do it here, but they will also prove to be quite useful to us later in the class, not in the beginning. but they essentially they relate to scalar functions u and v in very specific ways. Okay, so with that, I'll probably conclude. I think that covers quite a bit of what we're going to do in this class and some basic, maybe not that basic, vector calculus relationships and identities. So with that, I think we're pretty much ready to get started with the first lecture or the first video in this series on YouTube. Hopefully you are super excited, and I certainly am, so I look forward to it. So I'll see you in the next one. Thank you.